All right, thank you so much for this invitation. So I'm presenting this paper, which is joint with Jay Liu and Xiaoshen Mu, both economists. And I wanted to say that I would love for you to interrupt me during the talk. So this is probably the paper I've written that's closest to, let's say, real world issues. So things that you might sort of have feelings about, or which might touch on aspects of your actual life. And so to the extent that you have reactions like, maybe that's not the definition I have in mind, or, your results sort of imply something for a setting that I care about, those are all reactions I would very much like to hear. All right, so as many of you are well aware, algorithms are now being used to guide decisions in many high stakes contexts, ranging from who should receive bail to who should receive a loan. And recently in computer science literature, there's been a lot of attention on how these algorithms might be unfair, in the specific sense that the error rates of these algorithms differ systematically across different social groups. Okay, so one highly publicized incident of this was the 2016 ProPublica article that revealed that an algorithm which was being used to help guide decisions about who should receive bail, that algorithm was mislabeling non-white defendants as future criminals twice as often as white defendants. Okay, so this is a false positive rate for the algorithm that is twice as high for the Black population in this case as compared to the white population. Right, and since then there's been many more examples of this potential disparity of how the algorithm treats different social groups. So this is a recent paper that came out in Science regarding the properties of an algorithm that was being used to help decide who should receive a particular medical procedure. This one, I think actually Apple was subsequently cleared. Of course, these are always difficult empirical questions of actually demonstrating whether the algorithm is in fact behaving in some sort of discriminatory way. But the Apple card was accused of treating men and women differently. This headline is about hiring. So this is really, pervading all different aspects of these applications we were looking at a moment ago. All right, so, that may be troubling on its own, but fairness is not the only criterion we care about. Right? We also care about the algorithm's accuracy. An algorithm that was making mistakes equally for everybody, that's very fair, but, maybe that's also not the algorithm we want. And this paper is all about understanding the nature of the trade-off between those goals. Okay, so first, just to give you, an example for why this trade-off is sort of not that easy to think through, let me give you a stylized case. So here we have two populations, red and blue. Squares are people who are helped by given medical treatment. Okay, you're actually sick, you need the treatment. Circles are people who don't actually need the medical treatment, might even be harmed by it. All right. Now, suppose first that you're given no information at all about this population. Well, then, since I'll just tell you, you can count it, but there's slightly more squares and circles. If your goal is correct classification, what you would choose to do is to treat everyone. All right. That decision would lead to an equal error rate of 7/15 for both populations. And so, in a sense, it's not a very accurate algorithm, but it's a very fair algorithm. It's the same error rate for both groups. All right, now suppose that actually you get access to covariate X1, right? You get to observe this and your algorithm can depend on it. Well, one thing you might be tempted to do then is the following, right? You might say, well, look, I'm going to draw a line here. I'm going to treat everyone whose X1 covariate is on this side of the line, and I'm going to not treat everybody in this part of the population. So that would actually maximize your aggregate accuracy. But note that it's going to lead to this big disparity in the error rate for red individuals versus for blue individuals. So in fact, the red error rate is now dropping to 0, right? You're correctly classifying everyone in that population, while the blue error rate has actually increased relative to the rule that you would have chosen given no information at all. Okay. So introduction of this information X1 really creates a fairness accuracy trade-off where you now have to decide, well, do I want this algorithm which is more accurate but potentially less fair, or do I want to go with something like this one instead, which is going to lead to an error rate of 1/3 for both groups. Okay, so more fair, less accurate. And those are potentially difficult questions to resolve. All right. And just to demonstrate that, it's not that fairness and accuracy have to be in conflict with one another. Suppose now that you actually also gain access to X2. Right. Well, now you have access to this rule, which says treat everybody here, don't treat everybody here. So this rule is going to lead you to perfect classification. Error rates for both groups is going to drop to 0. So access to X2 is actually increasing both your ability to create fair outcomes and your ability to create accurate outcomes. So more generally, what the fairness accuracy trade-off is going to look like is going to depend crucially on statistical properties of the inputs. Right? How are the covariates you're observing correlated with group identity? How are those correlated with what you're trying to predict? And our question in this paper is how, right? What statistical properties does it depend on, and how does it depend on them? So specifically, we might wonder, for what kinds of inputs would, say, a utilitarian decision maker and a Rawlsian decision maker disagree about the best algorithm? Okay, in some cases, they need not. Some cases they will. When will they? Are there simple statistics, right? Summarizing this high-dimensional distribution, describing all the covariates and the relationship with what you're trying to predict. Are there simple statistics of that distribution that can tell us something already about the shape of the fairness accuracy trade-off? Okay. For example, one such statistic might be whether the covariates the algorithm has access to, in fact, reveals the group identity. And then finally, so this is a question that's been of recent interest in various policy sectors. So if we can choose to ban a covariate from use, right? A lawmaker can just come in and say, look, you're not allowed to use covariate X1 in your algorithm. When would it be welfare improving to do that? Right, so these are some of the example questions we'll answer, and we're going to answer all of these questions through the lens of what we're calling a fairness accuracy Pareto frontier. So essentially, we're going to be allowing for a broad class of different ways of trading off between fairness and accuracy. We're not going to commit to one of these as the right way of trading off between the two because we don't know what the right way is. Okay, so we're going to work with this class of preferences. We're going to look for all the points that are optimal for different preferences in this class, and that's going to be our frontier. All right, so any questions at this point about the high level of what we're trying to do? All right, so if not, here's the plan for the talk. I'm going to tell you about the framework we're using to think about this problem with. I'll characterize this fairness accuracy Pareto frontier for you. I'll tell you what the result looks like in the special case where the group identity is actually known to the algorithm. We'll talk about this question I just mentioned regarding when it's optimal to add or ban a covariate. Formally, we're going to be studying that by looking at how the Pareto frontier changes when we add or ban an input. And then finally, what I want to talk about is a variation of our problem where the designer doesn't have full control of the algorithm anymore, but instead gets to control only the algorithm's inputs. So we're going to have two individuals sort of interacting with different preferences. One gets to choose the inputs, the other gets to choose the algorithm. I'll say more when we get there. Okay, but we'll look at how many of these results extend. All right, so here's our framework. We have a single designer and a population of non-strategic subjects. Okay, by non-strategic, I mean that they're not actually going to take any actions. They're in the model only because we care about what we do to them. Each subject is going to be described by 3 variables. The first is a type, and I want you to think about this as what the algorithm is trying to predict. For example, in the medical case, the type might be your need for a medical procedure. Okay, second, the individual is going to be described by a group identity. Throughout, we're going to be taking that to be binary, so you're either red or blue. You can think about that, for example, as race. And then finally, the individual is going to be described by a covariate vector, okay, or for computer scientists, maybe we should call that a feature vector, right? The same thing. So this is just all the inputs that the algorithm might have access to. This is your image scans, the number of times you've visited the hospital in the past, blood tests, so on and so forth. And we're understanding X to be what the algorithm gets to see. Okay? That doesn't mean that the algorithm necessarily doesn't know Y and G, right? Because it might be that X actually partially or fully reveals either of these 2 variables, but formally we're taking X to be the actual variable that the algorithm gets to see. Okay, so now in the population, y, g, and x are random variables, and they're going to have some joint distribution corresponding to heterogeneity across subjects in this population. Okay, so that's a primitive. We're taking this p here. Okay. Now, each subject in our population is going to receive an outcome. For example, whether that medical procedure is in fact recommended to the subject. And the outcome for the subject is going to be determined based on an algorithm that the designer gets to choose. So formally, an algorithm is any mapping from the space of observable covariates, right? That's the space that this X belongs to, into the set of distributions over the action set. Right, so you can think about this as okay, this is a randomized algorithm. So given the covariates that you have, what is the probability that you're going to be recommended the treatment? Right, so I've been talking about the medical example, but very naturally we can think about this framework in the context of all the other examples we've been discussing. So in the case of bail decisions, Y is whether the individual is high or low risk of crime. G might be race. A is the decision of whether or not to release the suspect on bail. X includes, so these are actually, by the way, real covariates that have been used in algorithms for these sorts of decisions. So criminal record, location of residence, psychological examinations, etc. In the case of credit scoring, Y is creditworthiness. That's what the bank would like to know. G might be gender. A is whether the borrower's loan request is approved. Again, you can imagine all sorts of covariates relevant to that decision. Okay, the final application here is job hiring. All right, so once we fixed an algorithm, how do we evaluate how well that algorithm does? So what we're going to do is take a primitive loss function that really you can choose for your setting. Okay, so we're going to allow for this to be a completely flexible mapping from the space of actions, true types, into real numbers. And because this isn't constrained in any way, there's actually two ways of interpreting it. So you can first interpret it as as an actual loss function, right? Something measuring the inaccuracy of your decision. For example, the very popular metrics of false positive rate, false negative rate, those can all be nested as special cases of this loss function. But since this isn't restricted to the positive reals, you can actually take the loss function to literally be the negative of the subject's utility. Right, which would accommodate a number of very different kinds of criteria. So, for example, maybe you want to be released on bail no matter what your true type is, right? Or you want to be hired no matter what your true type is, and those are things we can also accommodate using this loss function. Right. So now this next definition is going to be the most critical definition. What we're going to do is we're going to aggregate these losses within groups. So, fixing a group G, fixing an algorithm. The error for the group given the algorithm is simply going to be the expected loss conditioning on that group's identity. Right? So conditioning on your group identity being this little g, X and Y are still random, right? Corresponding to heterogeneity across subjects in that group. Whatever your covariates end up being, we're using this algorithm F to determine the action that's taken for you. Then we're using this loss function L that we discussed a moment ago to determine, again, the sort of cost of assigning that action to you given your true type. Right. So now we're going to have for each group then, so this ER of F is the average loss for subjects in group red. This EBF is the average loss for subjects in group B. And we're going to be interested throughout in these error pairs, which I'll more simply denote E of F. This is essentially what the designer is going to have preferences over. Okay, so what do those preferences look like? What does the designer care about? So we're going to impose only a very weak criterion constraining these preferences. So the weak criterion is the following. We're going to say that if it's possible to increase both accuracy and fairness, the designer should prefer that. Okay, so formally, if we have two different error pairs, E and E prime, where E involves a lower error for both groups compared to E prime. Okay, that corresponds to higher accuracy. And moreover, the gap between ER and EB is less than the gap between the group error for group R and group B under E prime. and at least one of these inequalities holds strictly. Okay. In that case, we're going to say that E Pareto dominates E prime, and therefore the designer should prefer E over E prime. But given this constraint, we're not going to impose a specific way of completing. So this is the partial ordering, right, over error pairs. We're not going to favor a specific way of completing it. Instead, we're going to allow for all preference orderings that do agree with this Pareto dominance ordering when it has byte. All right, and that's, so let me just show you graphically what that means. Okay, so suppose we're going to be looking at a lot of figures like this. So the x-axis is group R's error. The y-axis is group B's error. Let's consider this point E prime. So by the first notion of Pareto dominance that might come to mind, you might say, well, I think everything in this blue box is better, right? That would just correspond to reducing errors for both groups. If that's all you cared about, then indeed everything here would be better. Introducing a fairness consideration here means that we're chopping off part of this region, right? So points here have the property that although group errors have both gone down, the gap between those errors has actually increased relative to this original E prime. So we're not saying that these points are worse than E prime, right? You very well may still favor these points over E prime. In fact, most of our designer preferences will. We're just not requiring you to favor these points over E prime, okay? We're taking the more conservative position that at least everything in this blue region, which has the property of both higher accuracy and again, higher fairness, and that this gap has shrunk, you must at least prefer these points over E prime. Right.
Annie?
Yeah, go for it.
Can you go 2 slides back? I have a question.
Yes, happily. This one?
Yes. So this loss function, do you assume that this loss function is known to the learner? Because in those situations that you've just described, such as lending, hiring, recidivism, you can think of situations where you have this one-sided feedback problem. Right, you only observe feedback for the people that you actually give out the loan to, or for the people that you set bail to. So in practice, you can think of a situation where the learner does not actually observe its own loss. So do you assume that
yeah,
subject
absolutely.
to the prediction?
That's a great question. Sorry, first of all, who is asking the question? I actually can't see usually the
Yeah, hi.
Okay, great, hi. Okay, yes, that's a great question. So throughout this paper, we actually just assume that this distribution P, I guess you didn't actually mention this joint distribution, but I interpreted your question as being related to that too. So this distribution P relating the variables, right? We're assuming that this distribution is actually known to the algorithm designer. We also are assuming that this loss function is known. I mean, so for the first part of the talk, it's really just a single agent problem where the algorithm designer is optimizing their own criterion, their own utility function. So it makes sense in that situation that you would know what you care about. Near the end of the talk, once you introduce the 2 engines, then that assumption stretches a little bit thinner. But I understood your question really to be more about this part, right? Because if you don't know what P is, if you're actually learning it from data, then it actually does matter if the data that you're getting is sort of lopsided in some way. Yeah. So I think that's super interesting for potentially for follow-up work. So here we just wanted to start with the simplest case where this distribution is actually taken as a primitive. It would be very interesting to ask if you don't know what P is, if you have to learn about that from samples, how will that affect everything else that I say? Or relatedly, you can even ask the question of what is the optimal way of sampling from this distribution, right, to achieve certain fairness accuracy goals. But for now, that's something we're putting aside.
Thanks.
Thank you. Okay, great.
So, Annie,
yeah.
can you go back to the rectangle you showed?
Mm-hmm.
So what's the small triangle below? What is it?
The triangle below, this one here?
Yeah.
Yeah, so these are, again, also points that are going to be, they're increasing the gap between the 2 group errors. So this line is on the same, so this distance between this line here and the 45-degree line is the same as this distance here. So all
Got
the
it.
points
Thank
here.
you.
Okay, thank you for the question. Okay. So we have this criterion, and there's going to be many different kinds of designer preferences that are going to be consistent with that Pareto dominance ordering. So let me just show you a few. So first, maybe you're a utilitarian designer, right? You don't actually care about fairness across groups. We're allowing for that, all right? So what you would like to do is minimize the aggregate error in the population. Your indifference curves are going to look like lines like this, where as they move towards the origin, you're happier off. And let's just quickly verify that this is in fact consistent with the Pareto dominance ordering. So again, take this point E prime. Okay, you're indifferent between E prime and all of these points, but note that in fact, all of these points do correspond to an improvement from your perspective, because if you draw the lines between any of these points, they're all going to be more inner compared to this original line. All right, so we're allowing for the utilitarian designer. You might be Rawlsian, right? You might say, look, what I care about is the welfare of the worst off group. So I'm going to look at the larger of the two group errors, and I want that to be as small as possible. Okay, so this is a little bit confusing because actually everything, we're writing these criterion as kind of like errors. So you always want to minimize this, not maximize this. Okay, so I want to minimize the worst off error. And again, we can see that this respects the Pareto dominance ordering. So now your indifference curves look like this, right? For any of these lines, you're indifferent between all the points on them. Starting from E prime, again, we can verify that all these points correspond to points on inner indifference curves that are better for you. And then actually going to Mihal's question from a moment ago, let's consider the egalitarian designer. So this is somebody who says, I don't care about accuracy. I only care about equity, all right? I only care about the gap between the two groups' errors. If there's a tie, then I'll care about accuracy, and I'll use accuracy to break the tie. So in this case, these indifference curves are these lines that are parallel with the 45-degree line. So I'm indifferent between E prime and all points on these two lines. And you can again verify that all these points are the ones that are, that all these points which Pareto dominate E prime are indeed also better according to your criterion. All right, so that's the designer's preference. Let's now talk about what's actually feasible for the designer to implement. So let's define script F here to be the set of all algorithms. So again, remember, this is all mappings from the set of observed covariates into distributions over the action set. The feasible set then, given X, is simply going to be all error pairs that can be implemented by some algorithm, right? So we're varying over these possible algorithms. We're looking at the error pairs that they induce. And then very naturally, the Pareto set then, given X, is simply going to be all error pairs within the feasible set that are Pareto undominated. So there must not exist another feasible error E prime, which Pareto dominates this E. And this is really the object of our analysis. We're going to be characterizing what the set looks like and how that depends on X. All right, so any more questions about definitions or notation before we go into the results? Okay. All right, so let's characterize this. So first I need to give you a couple of preliminary definitions actually for important points in the feasible set. Okay, so let's fix a covariate X. Suppose we only cared about group G, okay, some group G here. We're going to minimize then just for this error, e.g. We're going to look for the point in the feasible set that minimizes e.g., not caring about what we do to the other group. That point we're going to call G of X. So we're going to have 2 points like this, one for group R and one for group B, right? Okay, likewise, we could also ask ourselves, what happens if we only care about fairness? So we're going to find the point in the feasible set which minimizes this gap between the two errors. In the case of ties, we're going to break ties in favor of accuracy, returning unique points for Rx, Bx, and Fx. Right, so these points are very easy to compute, right? So suppose this is our feasible set here. what is Rx? Well, Rx is going to be the point that's the most to the left, right? Because here we have ER on the x-axis, group R's error. And so this is going to be the point that minimizes group R's error, okay, which is also feasible. What's Bx? Well, that's going to be the point that's as bottom as possible. And what's Fx? Well, that's the point that's closest to the 45-degree line. Okay. Now, notice something funny about this, this picture. So if we consider Bx, which remember we defined to be the point that's group B's favorite point, if we look at that point is actually above the 45-degree line. So what that means is that at this point, which is group B's favorite point, group B actually has the higher error relative to group R. Now that's certainly possible. That property ends up being really the key statistical property in all of our results, so we're going to give it a name. We're going to say that covariate X is R skewed if group R's error is strictly below group B's error at group R's favorite point, and moreover, group R's error is weakly below group B's error at group B's favorite point. Okay, so yeah, go for it.
Is it necessarily the case that EX, the feasible set, is convex?
Yes, it is. Yeah. Okay, so thanks for the question. So I'm sort of leaving out some of these technical details about this the set, but yes, we do in fact know that it's convex. In fact, it's a convex polygon, as I've denoted it, assuming that X is finite valued. Okay, otherwise it's really the same idea. It's just that this might be a smooth boundary.
Mm-hmm. Thank you.
Thanks for asking. Okay, great. So this is an example of an R skewed covariate. If we just reverse the groups, we're going to call that B skewed. And sorry, just one last comment on the convex, right? So the reason it's convex is because if we have 2 points that are implemented by 2 algorithms, we can essentially take a mixture of those two. We can randomize over them, right? And that's going to give us the error pairs in between. Okay, so now if the covariate is neither R skewed or B skewed, then what we're going to say is that the covariate is group balanced. That's going to correspond to a case where Rx is above the 45-degree line while Bx is below. And again, because this ends up being so critical in our results, I just wanted to give you some more intuition for when we might see skew that looks like this. So first, here's just a very simple example. Suppose y is either 0 or 1, and suppose the uniform, the marginal distribution of y is uniform for both groups. Let's take classification error as our loss function. And suppose your covariate X has the following property. So conditional on group R, this is going to be the joint distribution of X and Y. Conditional on group B, we've got this one over here. And what we can see is that X is a more accurate signal of Y for group R than for group B. So what is Bx? Well, Bx is the point that minimizes error for group B. It's pretty clear how we would do that. We would map X is equal to 1 into the action 1. We would map X is equal to 0 into the action 0. That's going to give group B an error of 1/3, but notice that that algorithm is also the one that is best for group R, and because X is a more accurate signal of Y for group R, we're actually going to get a lower error using the same algorithm for group R. And so this is precisely the kind of case where we would see skew. Okay. And in the real world, what does skew mean? Or this is something we might actually imagine emerging in practice. So yes, for a couple of different reasons. So first, we might have covariates that are systematically more informative about one group than another. So this is a real example here. If you look at the number of past hospital visits as an indicator for need of care, right, like how sick are you? That covariate is more informative about need of care for wealthy individuals compared to less wealthy individuals, because less wealthy individuals have a harder time getting to the hospital when they're sick. So that covariate is informative about both groups, it's just more informative about one. You condition on it, it's going to reduce errors for the wealthy population faster than for the non-wealthy population. Here's another example. This joint distribution for the variables P, I've been taking that as some sort of true objective distribution, but we could also interpret it as a prior that's informed by historical data. So again, considering the medical context, suppose we're trying to predict whether you have a specific disease. Suppose all of the experiments in the past have involved male subjects. Well, in that case, now conditioning on any symptom profile that we have, it very well may be that your beliefs are more certain for men than for women. Okay, so again, this is still informative. It's just that you're going to reduce errors for one group faster than for another. Okay, so now let's see how this property of skew matters. So what's going to happen is that we're going to have Pareto frontiers divided into two categories, depending on whether this covariate X is group skewed or group balanced. So let's first consider the case of group skew. So this is the same figure we had from a moment ago. In this case, the Pareto frontier is going to be that part of the lower boundary of the feasible set, connecting Rx to Fx. So again, remember that's group R's favorite point, and this is the fairness maximizing point. In contrast, when X is group balanced, the Pareto frontier is now going to be that part of the lower boundary of the set, connecting Rx to Bx. And note, by the way, that in this case, Fx is always going to lie on the 45-degree line. So it's always going to be possible to completely eliminate differences in group errors. Okay, so that's kind of neat on its own. We've learned something about what this frontier looks like. What does that imply for these policy questions we've been interested in? Okay, so here's one very immediate implication that we can essentially read off of the diagram so far. Okay, and so it's an implication for what kinds of accuracy fairness trade-offs are going to be relevant. So consider the following comparison. You could either have the error pair 1/2, 1/2, or the error pair 1/3, 1/4. Right. Now, note that E prime involves a higher error for both groups, but it improves unfairness. All right. Okay, so I don't know what your personal reactions are looking at these two error pairs. So certainly, many people have the reaction of this is a very obvious comparison. How could you possibly prefer E prime over E, because E makes everybody better off, right? Okay, so that's one very reasonable reaction. If you are somebody that, let's say if you're a pure egalitarian, okay, you just care about equity, that would be an extreme case in which this comparison is also very easy, right? You would say, well, definitely I prefer E prime because I've completely gotten rid of the gap in errors. Okay, and then in general, which of these two you prefer is going to depend sort of, very sensitively on whether you place sufficient weight on these equity considerations. So, regardless of where you end up standing, I at least personally feel like this is a pretty sort of fraught question, right? Like, if you really need to make this decision, it's not a very pleasant one to make. Unless you think that this is very evident, but let's consider like maybe a group decision, right? So there might be different people with different views. It certainly feels very controversial. So, it's controversial. Does it actually matter? And we can use our results from a moment ago essentially to answer when it does. So first, let's just formalize this. We're going to say that X exhibits a strong accuracy fairness conflict. If there are 2 points, E and E prime, that can be compared in this way. So E involves lower errors, again, for both groups, but this bigger gap between the two groups' errors. All right, so let's go back to these figures we were just looking at. Well, we know that in the group balanced case, the Pareto frontier consists entirely of these negatively sloped lines connecting Rx to Bx. So by virtue of these lines being negatively sloped, we immediately know that there cannot possibly be 2 points here where one point has higher errors for both groups. That's just not going to happen. In contrast, in this case where we have the skewed covariate, as long as Bx and Fx are not the same point, okay, then we do have a positively sloped line. And every pair of points on this part of the frontier do in fact represent a strong accuracy fairness conflict, right? One of the points is going to involve higher errors for both groups, but lower gaps. So we immediately see then that X exhibits a strong accuracy fairness conflict if and only if it is group skewed. Right, so going to an imaginary conversation with a policymaker, right? Suppose the policymaker comes to the academic and says, I have the policy proposal. This would decrease accuracy for both groups, but increase fairness. So in principle, you could reply by getting into a very long conversation about ethics and philosophy. Okay, that might be fun separately, but you don't have to. You can reply more simply, are the inputs to your algorithm group balanced? Right. Note, by the way, that group balanced is something that can be empirically verified given data from this joint distribution. And if the answer is that in fact the covariates are group balanced, then the answer is really quite straightforward. You can say, look, your proposal is necessarily going to end up off of the Pareto frontier. So it doesn't matter what your fairness accuracy preferences are. You could even be the pure egalitarian who only cares about equity. You still shouldn't want to do this. Right. In contrast, if the reply is that the covariates are group skewed, then it's more complicated. And if the policymaker cares sufficiently about fairness relative to accuracy, then the proposal may potentially be an improvement relative to the policymaker's goals. All right, so any questions about this result?
So isn't skewed X means that, we can eliminate it, but just, including the group as a parameter?
Sorry, I didn't follow that question. If X is skewed, then we can what?
If X is skewed, then I can add to my classifier parameters that they're belonging to either group, okay, and then it is not skewed anymore. No?
Great. Yeah, absolutely. Okay, so
or
you're
some
saying
other
that,
variables that solve it like in a non-direct way.
okay, so good. Actually, this is exactly going to segue into the next part. So you're asking what happens essentially if I add in, well, I guess you're asking two things. So one, if I add in group identity, does that make it no longer skewed?
Yes.
Right. Okay, I'll be able to answer that then in the section. And then second, just in general, is the case that you can affect skew by adding in and taking out covariates, right? So to the second question, the answer is absolutely yes. So so skew is a function of X, right? As we modify X, then definitely we can modify skew. So you can add in, so for example, right, if you are in this situation where you have a group skewed covariate and maybe you don't like the existence of this positively sloped line segment, one thing you could do is add in more inputs that make this in fact group balanced, and then that sort of conflict goes away. We don't have results, however, on in general what kinds of covariates move us from a skewed domain into a group balanced domain, but that could be an interesting separate question to look at. Adding in group identity actually doesn't do it. So let me tell you what happens in that case. So suppose that that G is revealed by X in the sense that conditioning on the value of X, G has a degenerate distribution. That could be because G is directly an input into the algorithm, it's just one coordinate in X, or it could be because G is perfectly correlated with proxy covariates in X. So in that case, our results simplify actually. And we have that the feasible set now becomes a rectangle whose edges are parallel to the axes. And we have that the Pareto frontier now is the line segment connecting this point, which is simultaneously optimal for group R and for group B, to the point which is fairness optimal. Okay, so this is actually a skewed case. Right. So why does it look like that, by the way? So what's special about the group balanced case is that essentially now you can set two algorithms, right? One for group R and one for group B, and these two algorithms don't have to bother each other, right? So I can flexibly reduce the error for one group without needing to change at all the error for the other. In general, that's not true, right? So if I don't know group identity, my hands are tied. All I can do is change what I do at these different covariates. But it very well could be that, if say at some covariate, group B's favorite action is 0, group R's favorite action is 1, then helping one group necessarily involves harming the other, right? In the case where X reveals G, that goes away. And that's exactly why we have a single point, which is now simultaneously optimal for both groups R and for group B. All right, so again, things we can just learn by directly looking at these frontiers. What we discover is that in this case, where X reveals G, the Pareto frontier becomes completely Rawlsian, right? The disadvantaged group always gets its minimal feasible error. So in this case, the disadvantaged group is group blue. And you see group blue everywhere on this Pareto frontier has to get the lowest possible error it could get. That part doesn't depend on the details of your fairness accuracy preference. Okay, so where your preference actually matters then is only insofar as what it determines for the more advantaged group. So if you're a utilitarian, then you're going to prefer this Rx is equal to Bx point. I mean, that's really great from your perspective because you really get to do what's best for both groups. As we range towards a designer who cares more, who's more egalitarian, we're going to get this designer sort of intentionally increasing the error for the advantaged group up until the point that the advantaged group's error is the same as the disadvantaged group's error. Okay, but if you're the disadvantaged group, really, you don't care what the designer's preferences are. You already know what your payoff is going to be. It's the same no matter what. All right, any questions about that part? Okay. So if not, let's turn to this question of what happens when a covariate is banned. All right, so an important regulatory question is, whether all inputs should be permissible inputs into algorithms, or whether there should be laws essentially saying, you're not allowed to use a certain input. And in a sense, this is not really a new question. So certain group entities have been banned for a very long time in consequential decisions. So for example, race and religion are banned in the United States for hiring and bank loan decisions. But this question has kind of acquired new life more recently, in part because of these algorithms with these sort of black box uses of these covariates, and also just other recent concerns. So for example, the University of California recently decided to ban test scores as an input into college admissions decisions. So this is a covariate that's not even group entity, but it's one that is being considered for one that the regulators are potentially considering as again, outright, you're not allowed to use this. Okay, so we can certainly study this question using our framework. So what we can do is we can split our covariate vector up into two parts. X here, we're going to call the sort of approved part, the part that's not controversial. X prime is going to be the covariate that's under question. And what we're going to be doing is comparing X and X prime as potential input vectors. And in the paper, what we look at essentially is how does the Pareto frontier given X alone compare to the Pareto frontier given both X and X prime. Okay, so now I don't have time to really go through all the different versions of this result that we have. But what I can do is show you the special case where X prime is in fact equal to G. So essentially we're asking, what happens when you ban group identity? Okay, so the thought experiment behind this question would be the following. A policymaker comes to you and says, I have an algorithm for predicting need of care. That algorithm uses medical records and group identity to determine treatment. But I'm considering removing use of group identity as a permissible input. Should I do that? And the answer, again, turns out to depend crucially on this property of group balance. So let's consider first a covariate X, which is group balanced. Well, then by our previous results, we know that the frontier looks like this, right? This is the feasible set. Here's a frontier from Rx to Bx. What happens if you were to add group identity? Well, XG certainly reveals G because G is an input in that vector. So now, again, using our previous characterization results, we now know that the feasible set must become a rectangle. Okay. Moreover, this is less obvious, but let me just tell you that is true. This is the smallest box enclosing the original feasible set. So in particular, the left-hand edge intersects with Rx. This bottom edge intersects with Bx. And therefore, this is the frontier, the new frontier down here, right? It connects our bottom left endpoint here to this fairness maximizing point here. And the first thing to see then, comparing this Pareto frontier when you're given both X and G to this Pareto frontier when you only have access to X, is that the two Pareto frontiers do not overlap. So what that means is that there's a uniform Pareto improvement. For every point on the original frontier without group identity, we can find another point on the frontier with group identity that actually Pareto dominates it. So this means that it doesn't matter what the designer's fairness accuracy preferences are, right? You could be utilitarian, you could be at the other extreme and egalitarian. Oh, sorry, that's a typo, that should be G, right? Taking away group identity from your algorithm is going to make you worse off no matter what. That's the case for a group balanced covariate. What happens if the covariate is group skewed? So here again, we have depicted an R skewed covariate X. Again, we know that the frontier looks like this, right? It's connecting Rx all the way to the fairness maximizing point Fx. Same as before, adding in group identity makes this feasible set a rectangle. But now, this new Pareto frontier given group identity does intersect with the original frontier, right? Remember, we said that the lower, this lower edge of the feasible set is the one intersecting Bx. Okay, so we have this intersection, meaning this is not a uniform improvement. Specifically, if you were somebody who preferred Bx, right? If that's your favorite point on the old frontier, adding in group identity is not going to help you to improve your payoffs. And in fact, if we sort of force you to use group identity by choosing some point which is made available that wasn't available before, so one of the points here, right? All of those points are going to be worse off for you, strictly worse off for you compared to this point Bx, which doesn't use group identity. Okay, so then going back to this conversation with the policymaker, if the answer is that the medical records are group balanced, then again, the answer is quite straightforwardly, removing group identity as an input makes you worse off. It doesn't matter what your fairness accuracy preferences are, you should use it. If the answer is that the covariates are group skewed, then details of your fairness accuracy preference do in fact matter. Okay, so just a couple of nuances and qualifications. So our results give conditions under which adding this new covariate is welfare improving across all designer preferences. That doesn't mean that the designer preferences don't matter, right? So depending on what your preference is, you're going to want to choose a different algorithm that uses that covariate, right? It's simply that you do want to use the covariate in some way. The other qualification is that here we've assumed that the designer has complete control over the algorithm and hence complete control over how the new covariate is used. So what we do then, and let me just quickly check on time. So I have about 10 minutes, is that right? Okay, so I think in the...
yes, including questions.
Oh, I see, okay. Okay, well, I don't
That's
know.
fine, you can go.
Okay, all right. Yeah, so I'll just keep on talking, but again, feel free to interrupt me with questions as I go. So in the last 10 minutes, I'll tell you about this variation of the problem that we've looked at, where the designer doesn't get to choose the algorithm, you only get to control the inputs that go into the algorithm, for example, by making certain covariates illegal. Okay, so remember again, our algorithm is this map from the covariates into this randomized action. And so far, we've assumed that the designer gets to choose that algorithm. Okay, now let's suppose that actually that's not true. There's some other agent that chooses the algorithm, for example, this bank manager. And that other agent is only going to care about accuracy, right? So maybe the bank manager only cares about profit. And we choose a loss function that matches that. The regulator, however, can influence this algorithm by controlling the inputs to the algorithm. So instead of assuming that X gets directly fed into this algorithm, we're now going to suppose that the regulator can first garble the covariate. Okay, and I'll be more precise about what I mean by that in a moment. But essentially, you're going to choose some sort of noisy transformation of this covariate. And that noisy transformation is all the bank manager gets to use in the algorithm that the bank manager will subsequently choose. All right, and we're going to suppose that the regulator may have fairness concerns, while again, this agent choosing the algorithm does not. All right, so what's the space of things that the designer can do? Well, remember that a garbling is any map from the original covariate values into distributions over new covariate values. Okay, let me just give you a couple of examples. One possible garbling is to return the original covariate as it was with probability 1. So that garbling just, you're not even reducing the information, you're just giving it back. Another possibility, this one's very policy relevant, is to drop an input. So suppose we initially had this covariate vector x1, x2, x3, you could say, look, I'm just going to take away x3. You can't use that in your algorithm. Okay. Another possibility is to add noise. So whatever x was, we're going to add some independent noise epsilon. A final possibility is to just take away all information entirely, right? So whatever x was, we're going to map that into some constant, okay, which doesn't depend on the value of x. Okay, so for those of you who've worked in differential privacy, right, this is probably familiar from that context. All right, so now for each garbling T, since we've assumed that the agent only cares about accuracy, what the agent will choose is the algorithm FT that maps each realization of T of X into the Bayes optimal action, right? So the conditioning on this value for this garbled covariate, what is the action that minimizes my expected loss? So this FT is the algorithm that this agent will choose. And therefore, we can redefine the feasible set in the Pareto frontier as follows. So the feasible set we call this problem Bayes design, that's going to correspond to all error pairs that are induced by algorithms FT corresponding to garblings T of X. All right, so just one more time, instead of varying over algorithms, the whole space of algorithms, we're now going to vary over the space of possible garblings of X. For each garbling T, we have a corresponding Bayes optimal algorithm F of T, and we're looking at the error pair that's induced by that algorithm. Okay, the Pareto set, again, is going to be the set of all feasible points, now feasible defined using this calligraphic E star of X, right? All points in this set that are Pareto undominated. Okay, so certainly we're imposing some sort of constraint here relative to the original problem, but how constraining is that constraint? In particular, we might ask, under what conditions is it actually without loss to have access only to control over the algorithm's inputs, in which case this new Bayes design frontier would actually be equivalent to the original frontier achieved under full control of the algorithm. And it turns out that that actually happens under pretty weak conditions. So let's first define E naught to be the best error you could achieve as utilitarian, given no information at all. Okay, then we have the following result. If X is G skewed, then we have this equivalence between the two Pareto frontiers. If and only if aggregate error at the special points Gx and Fx that we've been discussing all the way through, if at those 2 points, this G corresponding to this G here, right? If at these 2 points, aggregate error is weakly less than E naught. Okay, so in words, control over inputs only is without loss, if and only if a utilitarian prefers these points Gx and Fx over the best point under the prior. If X is group balanced, a similar result, right? Again, we have equivalence of these Pareto frontiers if and only if the aggregate error now at Rx and Vx are both weakly less than E naught. So again, this utilitarian prefers these points over what the utilitarian could achieve with no information. All right, and what's going on is the following. So let's define H to be the half space, including all error pairs that have a smaller aggregate error compared to this E naught, right? So this, remember, PR and PB are the fraction of the population in group R and in group B. Okay, now clearly, because the agent is going to do what's optimal for the agent, right? Again, from this utilitarian perspective, given whatever information you give the agent, you can't make the agent do worse than E naught, right? At worst, the agent could just throw away the information you give you and still achieve E naught. So certainly it's got to be the case that every error pair in this base feasible set belongs to the intersection of the original full feasible set in this half space. What's less obvious, but turns out to be true, is that every error pair in this intersection also belongs to the base feasible set, meaning we can find a garbling of X such that that error pair is implemented by this garbling. Okay, and in a figure, this is what this, okay, so those two parts then, right, give us these equivalences. So the base design feasible set is exactly the intersection of the full design feasible set in this half space. Likewise for the Pareto frontier. And in a picture, this is what it looks like, right? So remember, these were the two figures we've been studying so far. Suppose this was our original full design feasible set. What we've introduced now here is this half space corresponding to all error pairs that improve upon the prior for the agent. And the new feasible set is just this intersection here. And here, so note that the original Pareto frontier belongs to this half space, right? So in fact, this is a case where informational constraints are without loss. Any point here on this Pareto frontier that you wanted to achieve and could have achieved by choosing some algorithm, you can now achieve that by finding the right garbling to give to this agent. And you can see how the previous result appeared, right? Why these points Rx and Bx matter, because essentially all we have to check now is whether Rx and Bx lie to the right side of this line. As long as they do, the whole frontier is achievable. Okay. This is an example where it's not the case that the whole frontier is achievable. So here the half space now cuts into the original Pareto frontier. So if your favorite point was one of these points up here, okay, you could have achieved those points if you had control over the algorithm. Since now you don't, you're not going to be able to get your favorite points. These designers, however, will still be able to get their favorite points. So we've got like essentially a shrinking of the Pareto frontier, but not a strict worsening of it. All right, so comments on these results. So they depend critically on our assumption that the designer has access to a fully flexible garbling of the inputs. If you only give the designer the option to ban or permit, things will look different. Note also here that we've assumed that our agent also respects the original Pareto dominance condition because the agent is utilitarian. In principle, these results could change if, say, the agent wanted to increase errors from one of the groups, right? If the agent is adversarial this way, then this result is not in general going to extend. Okay, so am I basically at the end? I'm just trying to see if I have time to go through this. I'm happy to conclude, or do I have 1 or 2 minutes left, or am I basically?
Yes, please go
Okay.
ahead.
All right, then I'll just quickly talk about related literature. Okay, so there's a huge literature in computer science on algorithmic fairness. This is a very incomplete list of some of the earlier papers in this book recently by Aaron and Michael. So let me just highlight a couple of the key differences and contributions relative to this literature. So first, so my understanding is that one of the more common approaches in this literature is to maximize for accuracy subject to some sort of constraint on fairness. We're taking this different approach of instead characterizing this whole Pareto frontier between fairness and accuracy. Second, we work with this more general formulation of error that also includes an interpretation as utility or group payoffs. And that allows us to connect to this older literature in economics and philosophy that thinks about distributive justice and essentially how to trade off between these sorts of goals. And then finally, in this last section that I mentioned with Bayes design, right here, this is actually building on using tools from the information design literature, where we're formulating this problem of choosing inputs as one of choosing these garblings. And so in economics, in econ theory, there hasn't really, this algorithmic fairness consideration is quite nascent. In empirical economics, there's been some recent nice work on these problems. So these are some of the papers I've listed here. So essentially doing a careful analysis of some of these algorithms and looking at whether they do in fact treat groups differently. Okay, so then just to conclude, what have we learned? Ethics in high-dimensional distributions are hard, but in some cases we can use simple summary statistics to make statements that hold over all reasonable designer preferences. Okay, so thank you again for the invitation and for your time. I'm happy to stick around if there's questions.